All right, so now I have some questions for you. So here's the first one. Two marbles, one twice as heavy as the other, are dropped to the ground from the roof of a building. And again, if they don't say anything about drag, we ignore it. Just before hitting the ground, the heavier ball has blank. All right, so you pause your video and figure it out. Okay, we're back. So the answer, all of the answers talk about kinetic energy, right? So kinetic energy is 1/2 mv squared, or p squared over 2m. Okay, so we have two marbles dropped from the same place, right? And so right before they hit the ground, the velocities are the same, right? Because the acceleration due to gravity is constant. So the velocities are the same in absence of air. However, the question is about kinetic energy. Kinetic energy 1/2 mv squared. So the velocities are the same, but the masses are different, right? One is twice as massive as the other one. So therefore, the kinetic energy one has to be twice as much kinetic energy as the other one, right? Just because the masses, but the velocities are the same. Okay, another one. A block initially at rest is allowed to slide down a frictionless ramp and attains a speed of v at the bottom. To achieve a speed 2v at the bottom, how many times as high must the new ramp be? So, let me give you a hint. Mechanical energy conservation, right? There's no friction. I mean, frictionless ramp. As soon as you see that frictionless ramp, yes. So, mechanical energy conservation. So, pause your video and figure it out. Okay, we're back. So k plus u initial equals k plus u final. It's at rest initially, so that's 0. U is just mgh, or mgy, whatever you want to call it. At the bottom, u is 0, so we have 1/2 mv squared, right? So this potential energy was transformed into kinetic energy. Okay, so we want to get a speed of 2v, right? All right, so if you put 2v in there, 2v squared is 4v squared, right? So in other words, if v goes to 2v, then kinetic energy goes to 4 times what it was originally, right? Because it's 2v squared, which is 4v squared. So this is increasing by a factor of 4. So that means that this has to increase by a factor of 4. So the height has to be 4 times as much. So easy it is with the mechanical energy conservation. Bing, 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 it's great. So, yeah, I'm trying to emphasize using this. All right, here's another one. A block is shot up a frictionless, there's that word, frictionless. That means mechanical energy is conserved. A ball is shot up a frictionless 40-degree slope with initial velocity v. It reaches a height, h, before sliding back down. The same block is shot with the same velocity up a frictionless 20-degree slope. On this slope, the block reaches a height what? Okay, pause your video, figure it out. All right, we're back. You should do this. You should be able to do this in your head. It's conservation of mechanical energy. Okay. K plus u initial equals k plus u final. The initial potential energy is 0, so we have 1/2 mv squared. When it goes as high as it can, it stops. So the kinetic energy is 0, so we have mgh. All right. So same block is shot, same velocity. So that means that this is the same. So that means that this has to be the same. Right? So what's going to be the height? The same, h. All right? Simple as that. Just h. So that's the answer, h. And again, wonderful. Oh, yeah, okay. All right. Now this is my favorite problem. For a while, anyway. The drawing shows an empty fuel tank being released by 3 different jet planes. At the moment of release, each plane has the same speed, and each tank is at the same height above the ground. However, the directions of travel are different. In the absence of air resistance, do the tanks have different speeds when they hit the ground? That's the question, all right? In the absence of air resistance, do the tanks have different speeds when they hit the ground? If so, which tank has the largest speed? I really wish we were face-to-face because I'd like to see how everybody votes. But we don't. So pause your video and figure it out. All right, let's do it. Now, what's the perfect, wonderful phrase here? In the absence of air resistance. If that is correct, mechanical energy is conserved. So we have K plus U initial equals K plus U final. Now, notice I was nice. I gave you hints. All right, so at the moment of release, same speed, and they're identical tanks, right? Same speed, same height, right? So this is the same for each tank. Now, when it hit, like right before it hits the ground, this U is 0. So all we have is 1/2 mv squared, right? Right? Well, if this is the same for all 3, guess what? This has to be the same, right? So the velocities are the same. The speeds are the same. Simple. Speeds are the same. And it's simple when you just look at this, right? Just for fun, yeah. All right. Just for fun, I did it with the kinematic equations. And I don't want to go through it, but just look at all the work. Look at I had to find the final speed for each situation. I had to do all that work, and I had to use this trig relation that I learned in high school. You know, sine squared plus cosine squared equals 1. So what would you rather do? All that work or this, which you can do in your head? So all I'm saying is this, you know, this here is incredibly useful. Incredibly useful. Okay, so there you go. All right, so we've talked about gravitational potential energy in gory detail. Well, there's other types of potential energy. For example, elastic. Some people call it elastic, some people call it spring. I call them both, you know, kind of inconsistent, but that's okay, right? But anyway, so here it is. You know, you can imagine having a mouse trap, and you pull it back so it has that potential energy, right? And so if the mouse comes up, bang, you know. Okay, so here. Okay, this is the wall. See, wall, right? That's the wall. The spring is attached to the wall. This is frictionless. You don't have to worry about that. And this is the block, which is attached to the spring. So basically what we want to do, you know, we just want to pull the block or push the block or something like that. All right. Now, we don't need the Earth, because will the Earth have any effect on this? Nah. And it's frictionless, so we don't have to worry about that either. So what we want to do, is we want to calculate the potential energy. Right? That's what we want to do. And we're going to use this again. All right, we're going to use that again. I should be better. All right, so the change in potential energy of the spring equals minus W interaction. Okay, now I told you last chapter that we were going to use a lot of things in this chapter, so I'm going to prove myself right. Okay, so let's do it. So the change in potential energy of the spring equals, I'm going to be kind of lazy, all right? U final minus U initial, okay? So I'm talking about spring, so I don't have to keep writing that. And that, according to that equation, equals minus the work, the interaction work. Now what's the interaction work? Well, the spring is pulling or pushing or something on the block, right? So spring on block, okay? Now, remember last chapter we did that crazy calculation? Well, that's why. So we can use it, okay? That's why. All right, so we want minus W. So W has this minus. So minus, minus, so we're just going to wipe out that minus sign. So we're just going to have K over 2 delta X final squared minus K over 2 delta X initial squared. Okay. All right. So what is U final? Well, U final has to be that. What's U initial? Has to be that, right? I mean, right. So it kind of makes sense, right? So what are we going to say? We're just going to say that U, so therefore, we're just going to say that U equals 1/2 K delta X squared. Ta-da! Right? Okay. So again, we would not have been able to figure this out if we didn't have this relationship. Right? That's the crucial relationship, because there's no great way to calculate, there's no direct way to calculate that, so we have to calculate the work instead, which is not so bad. Okay, so there it is, all right? So now you have two, right? You have mgh for gravitational, and you have 1/2 K delta X squared for spring. So there's two types of potential energy that we've discussed so far. All right, so let's say we have a system where we have gravitational potential energy and a spring involved. So now my favorite equation gets a little bit longer, right? We don't just have UG, we also have U spring. So what? So this is the mechanical energy conservation, right? We just have two types of potential energy. Now usually, we're going to be smart and have the spring horizontal, and so the UG initial equals UG final, so we can just scratch that, right? But you never know, Okay, so again, if there's no friction, no dissipative forces, mechanical energy is conserved, right? That's what this says. Mechanical energy is conserved. K plus U initial equals K plus U final. But there's two U's, whatever, Okay, let's use it. A spring-loaded toy dart gun is used to shoot a dart straight up in the air. And the dart reaches a maximum height of 24 meters. The same dart is shot straight up a second time from the same gun, but this time the spring is compressed only half as far before firing. How far up does the dart go this time, neglecting friction? Nice, right? That means mechanical energy is conserved, and assuming an ideal spring. So pause your video and figure it out, please. All right, what's the answer? Okay, 6. Why? So I have K plus UG plus U spring initial equals K plus UG plus U spring final. Okay, now initially, what's K? It's 0, right? We compress that spring. So that's 0. Okay, what's UG initially? 0. And we just have US, which is 1/2 K, what do we want to call it? Delta, I'm going to call it delta S or something like that. Delta S squared, okay? And then at the top, it stops, so the kinetic energy is 0. UG is mg height. And in US, when it gets to the top is 0 too, right? Okay, so that's what we have, right? So this delta S, that's how much the spring is compressed, okay? So 1/2 K delta S squared equals mgh. All right. Now it says the second time the spring is compressed half as far. Okay, half as far. So if this is half, what's a half squared? A fourth. So this is a fourth of what it used to be. So that means that this has to be a fourth of what it used to be. So initially, it went up 24 meters. The second time, when the spring is only compressed half as much, it's going to be a fourth of that. What's a fourth of 24? 6. Okay, 6. So that's how you do it. Isn't it great? I mean, it's hardly any work at all, you know. As soon as you see that word, neglecting friction, you should think mechanical energy conservation. Then you just write it down, and it's wonderful. Yeah, all right, there's our friend, right? Okay. Now, we've been making a big deal about how wonderful life is without friction. Well, what do you say now we get back to reality? And let's include friction. Ugh, I don't want to. All right, so now we're going to include friction. It's going to mess things up, but that's all right. I mean, it's reality. What are you going to do? Okay, so let's include friction, include air resistance. So here's that tall building again, right? Now, let's assume now that we're going to include air resistance, all right? So remember when I did this before, you know, I said that we start out with 10 joules here, 0, and then 10, right? And mechanical energy was conserved, so here I had 0, 10, 10. But now, friction, so mechanical energy is not conserved. So I'm going to just pick a number. So let's say instead of having 10 here, I have 9 joules, all right? So 10 joules went to 9 joules. Well, what happened to the other joule, right? What happened to the other joule of energy? Well, what do you think? If something is plowing through air, there's air resistance, and what happens? It gets converted to thermal energy, right? Heat, okay? So what I'm saying is, if we include air resistance, because it's a really tall building, then the 10 is going to become a 9, and the missing joule is going to be thermal energy, right? It's kind of wasted, you know? Thermal energy. And I showed you that the other day, right? When the space capsule plows through Earth's atmosphere, you know, it gets really, really hot. All right? So thermal energy. Okay, so now we're making life really complicated. So we used to have the change in energy of a system was delta K plus delta U, but now we're messing things up because we're including, you know, friction. So we have thermal energy. So now our equation gets even more complicated, but it's not so bad, all right? So delta E sys equals delta K plus delta U. Remember, there could be 2 more of these, right? But now we have delta E therm, okay? Yuck, all right? But notice something's important, right? The change in energy of the system is still 0. So the energy of the entire system is conserved, but since we have friction, you know, mechanical energy is no longer conserved, right? That's an important point. Let me repeat it. The energy of the system, the change of that is 0. So the energy of the system is constant, it's conserved. But the mechanical energy is no longer conserved because now we have, you know, friction, which leads to, or drag, which leads to thermal energy. All right? Okay, now, you know, all right, so we know how to calculate that, just 1/2 mv squared or p squared over 2m. We know how to calculate that, you know, the minus w interaction. How do we calculate that? Well, we learned that last chapter, you know, right? And we learned that last chapter, remember? Okay, so delta E therm equals minus w dissipative, like friction or something like that. So that's how we do it, all right? So instead of having, I mean, this is true, but we don't like that. So we're going to substitute minus w dis, right? Okay, so this is what we had. Now we're going to substitute minus w dis. So this is now our equation because, again, we can't calculate that directly. We got to do that instead. So this is the useful equation, right? The useful equation. All right, now let me show you a better way of writing that. I mean, it's very similar to what I did a few minutes ago. Okay, so we have delta K plus delta U minus W dis equals 0. So that's K final minus K initial plus U final minus U initial minus W dis equals 0. So I'm going to put my initials on the other side. So K final plus U final minus W dis equals K initial plus U initial. And then I'm just going to switch it because I want my initials on the left and my finals on the right. You don't have to, but I just like it that way. So K initial plus U initial equals K final plus U final minus W dis. So that is true, but this is more useful, you know? I mean, this is very similar to what we had before, but with mechanical energy conservation, but now we have this thing because we have friction, right? So this is a nice way to write this. It's just more useful when you solve problems. All right? Oh, yeah, and we did this last chapter, right? You know what? Here's an example, right? We're pulling a heavy box, a distance delta x across the floor. So there's the force pulling it, but there's kinetic friction as well. What's W dis? Well, you know, friction, right? And so Fk goes that way, delta x is that way. So it's Fk delta x cosine 180. Cos 180 is minus 1. And I mean, it better be negative, right? Since friction's not helping it, you know. And so W dis is minus Fk delta x. And therefore, what's delta E therm? The negative of that, so just Fk delta x. So see, this is a piece of cake to figure out W dis, you know. And so since we know that W dis equals minus that, we can figure out these delta E therms. So it's nice. Nice, nice, nice. All right, wonderful. Okay, let's see, what's that? 14. Okay, so at this time, I was going to do a really cool demo, but we don't have any tables, so I can't. Sorry, and it wouldn't work really good on the floor, and you really need two people to do it. Anyway, excuses, right? So I'm going to explain it to you, or describe it. So here's a tabletop. So on the tabletop, I put 2 meter sticks, like really close together, kind of like to use them as like a track. So it's kind of like this. So here's 1 meter stick. Now you're looking down on the table. Here's another meter stick. Okay. And then I have these solid spheres. They're like that size. They're really pretty big, you know, solid steel, right? And I put one here and one here. So one here and one here. And then I shoot them towards one another, right? So while I'm doing that, I have another student hold just a piece of paper right in the middle. Okay? All right. So we shoot these heavy, solid steel spheres. Bang, right? And so eventually, you know, they're going to smack right here, right? That's not again. All right. So they're going to smack right there. Now, you know, they had kinetic energy. Agree? And we're going to ignore friction here, you know, here. But they had all that kinetic energy. But then when they smack, there's no kinetic energy. It's right. It's zero. So the question is, and you know, the gravitational potential energy doesn't change. So when you have that kinetic energy, all of a sudden goes to zero. What happens to the energy? Well, so you do this demo, and like I say, I have a student holding this piece of paper, and I tell the student, as soon as you hear that smack, take the piece of paper and put it near your nose. They think I'm a little weird, right? And what happens is that this kinetic energy is converted into thermal energy. So what happens to a piece of paper, it actually burns a little hole in the piece of paper. So you can put it up to your nose, you can smell the burned paper. And then you can actually see the hole, all right? So it's kind of a cool example of energy conservation, right? All that kinetic energy has been transformed into thermal energy, and it burns the paper. So it's kind of cool, but oh well. Maybe I make a video one of these days. I don't know. Anyway. All right. One more question before we stop this video. A stone is launched upward into the air. In addition to the force of gravity, oh, this is a good one. Okay, you shoot a rock up in the air. In addition to the force of gravity, the stone is subject to a frictional force due to air resistance, drag. The time the stone takes to reach the top of its flight path is blank compared to the time it takes to return from the top to its original position. Woo, okay, so here's the wherever the starting point, and here's the ending point, right? And so we shoot it up in the air, and then it comes back. And what the question is, okay, and so there's drag, right? There's, for you to, okay, let's draw the force diagram. So this is on the way up. I'm kind of giving it away. Maybe I shouldn't do that, whatever, So on the way up, so the velocity's up. But what are the forces acting on it? Well, there's gravity. But look at when it's on the way up, what's the direction of the drag? Opposite, so it's down. So on the way up, the drag is down. That's drag. And the force of gravity is down, mg. Now on the way down, so that's up, right? Now on the way down, let's do the down. Okay, down. Okay, on the way down, velocity is down, right? No kidding. Okay. All right, so what are the forces acting on it? Well, it's going down. I mean, there's gravity. There's always gravity, right? But the velocity is this way, so what's the direction of the drag? This way, right? The drag is that way. I don't know if that helps, but it's true, all right? But anyway, so pause your video and figure it out. All right, let's talk about it. Okay, well, first of all, the answer. Smaller. Why? So let's just pretend, let's just say we have 10 joules right here. Now, without air resistance, we would have, this is kinetic energy, right? We shoot it up with a certain velocity. Without, agree? So if we had no friction, we'd have potential energy of 10 joules here, right? Okay, however, we have drag. So let's just make up a number. Let's say we've wasted 1 joule because of the thermal energy. So we only have 9 joules here, right? So that means we have 9 joules here. Now, when we're going down, we still have drag, right? We still have drag. Well, let's say we waste another joule, so we have 8 joules here, So this is kinetic. All right, so look. Here, we had 10 joules of kinetic energy, right? 10 joules. And so it's going fast, but it's slow, slow. But here, we only had 9 to start with, and it only went to 8. So where's it going faster? On the way up or the way down? Obviously, it's going faster on the way up. I'm just talking about speed, magnitude. It's going faster here than it is here because we waste a joule because of thermal energy, and we waste another joule because of thermal energy, right? Okay, so it's not going to, so it's short time, longer time, because more kinetic energy than over here. All right, let's quit. Make sure you think about that. All right, let's see. Can we go like 5 minutes?